Somewhere on a server right now, a piece of data is protected by a lock that would take the fastest supercomputer on Earth longer than the current age of the universe to pick. And yet a handful of physicists believe a new kind of machine could pick that lock in a single afternoon. That claim alone should make you pause, not because it is sensational, but because it happens to be true. And understanding why it is true takes us straight into one of the strangest ideas in all of science. To get there, we have to start with a piece of mathematics that most people have never seen, but that quietly governs everything happening inside every atom in your body. It is called the wave equation of quantum mechanics, first written down by the physicist Erwin Schrödinger. On the page it looks like an ordinary differential equation, the kind you might find in an engineering textbook. In practice, it is a description of how the universe actually behaves at its smallest scales. It does not tell you where an electron is. It tells you the odds of where that electron might be found if you decided to look. That single shift from certainty to probability is the seed from which an entirely new kind of computing eventually grew. For most of the 20th century, computers were built on a much simpler idea. Every calculation, no matter how complex, could be broken down into a long sequence of switches flipping between two states, off and on, commonly written as 0 and 1. A weather model, a digital photograph, a video game, a banking transaction, all of it eventually reduces to strings of these binary digits moving through circuits. This approach carried humanity from room-sized calculating machines to the device you may be listening to this on. It sent astronauts to the moon and built the internet. But binary logic has a hidden weakness. Certain problems grow so explosively complicated that no amount of raw processing speed can rescue you from them. Simulating how a moderately sized molecule bonds and reacts, for example, requires tracking so many interacting quantum states that a classical machine runs out of memory and time long before it runs out of the will to finish. Physicists noticed this bottleneck early. If a classical machine struggles to simulate a quantum system, perhaps a machine built directly out of quantum rules would not struggle at all. In the year 1980, a physicist named Paul Benioff proposed a theoretical model of computation that used quantum states instead of ordinary bits. He called it a quantum version of the Turing machine, referencing the abstract computing model that underlies all classical computer science. On paper, it seemed closer to a thought experiment than an engineering blueprint. Around the same period, the mathematician Yuri Manin and the physicist Richard Feynman independently arrived at a similar conclusion from different directions. Feynman, in particular, argued that nature itself was not classical, so if you wanted a computer that could faithfully model nature, you needed one built from the same quantum ingredients. His argument became one of the founding justifications for the entire field. A few years later, in 1984, two researchers named Charles Bennett and Gil Brassard took a very different piece of Feynman's insight and pointed it toward a practical problem: secure communication. They realized that the strange behavior of quantum particles could be weaponized, in the best sense, against eavesdropping. Their idea became known as quantum key distribution, and it remains one of the few real-world technologies built directly on raw quantum weirdness rather than on speculative future hardware. Here is the basic idea. Stripped of jargon, picture two people who want to share a secret encryption key over a public channel, fully aware that someone might be listening in. One sender encodes a string of bits into the quantum states of individual photons, tiny packets of light. The trick is that quantum states cannot be secretly copied or read without disturbing them. If an eavesdropper intercepts even a single photon to measure it, that act of measurement changes the particle's state. When the two legitimate parties later compare a small sample of their photons out in the open, Any tampering shows up as an unmistakable pattern of errors. If everything matches, they know their shared key is clean, uncompromised, and safe to use. If it does not match, they simply discard it and try again. What makes this remarkable is that the security does not rely on a problem being computationally hard to solve. It relies on a law of physics being impossible to break. That is a fundamentally different kind of guarantee, and it means quantum key distribution stays secure, even against a hypothetical quantum computer powerful enough to shred every other form of encryption in use today. This is not a laboratory curiosity anymore, either. Financial institutions and government agencies in several countries already route sensitive traffic through quantum encrypted links, quietly proving that quantum weirdness can be turned into ordinary infrastructure. So, if the underlying physics is this secure and this strange, why is quantum computing described as a threat to encryption rather than simply a shield for it? The answer lies in what a quantum bit actually is, and how it behaves differently from anything a classical machine can offer. A classical bit is binary. It is either off or on, 0 or 1, with nothing in between. A quantum bit, usually shortened to qubit, is not limited to a single value while it is being processed. Through a property called superposition, a qubit can hold a combination of 0 and 1 at the same time, in a mathematically precise way that only resolves into a definite value the moment it is measured. Before that measurement happens, the qubit is doing something closer to exploring both possibilities simultaneously. A simple way to picture this is with a locked door that has a 4-digit code. A classical computer guessing that code has to try each combination one after another, 0000, then 0001, then 0002, and so on, until it stumbles onto the right one. With 10,000 possible combinations, that could take a while, even at high speed. A quantum computer, because its qubits can represent many combinations in superposition at once, can, in principle, explore all 10,000 possibilities in a single pass, using clever algorithms to make the correct answer stand out from the crowd once a measurement is finally taken. This is not magic. It is closer to running every branch of a decision tree in parallel instead of one branch at a time. Superposition alone would already be a significant advantage, but qubits have a second property that makes things even stranger: entanglement. When two qubits become entangled, their states are linked in such a way that measuring one instantly tells you something about the other, no matter how far apart they are physically separated. Einstein famously distrusted this implication and referred to it, somewhat dismissively, as spooky action at a distance. Decades of experiments since then have confirmed that the effect is real, reproducible, and consistent with the predictions of quantum theory, even though it still defies simple intuition. Inside a quantum computer, entanglement lets qubits behave like a tightly coordinated team rather than a collection of independent switches. Information does not have to move piece by piece between them. Correlations that would take a classical machine enormous effort to track are simply built into the entangled system from the start. Put superposition and entanglement together across enough qubits, and the numbers become almost impossible to hold in your head. Roughly 300 qubits, working together in superposition, can represent more distinct combined states than there are estimated particles in the observable universe. That is not a loose exaggeration. It is closer to a rough consequence of pure combinatorics. Each additional qubit does not add to the computer's descriptive power. It multiplies it, doubling the number of states the system can represent. A classical computer's storage capacity grows in a straight line as you add more components. A quantum computer's representational capacity grows exponentially, and it does not take many qubits before that curve shoots past anything nature itself appears to contain. It helps to see just how quickly ordinary probability spirals out of control, because it explains why this exponential growth matters so much. Flip a coin 20 times and write down the exact sequence of heads and tails you get. There are a little over 1 million possible sequences of that length. So the odds of matching someone else's exact sequence are roughly 1 in a million, worse odds than most raffles. Now stretch that same coin flipping experiment out to 266 flips. The total number of possible sequences at that length is to multiply by itself 266 times. A number so large that it exceeds the most commonly cited estimates for the total number of atoms in the observable universe. If every person on the planet, all 8 billion of us, had a computer capable of checking 10 billion sequences every single second, and we kept every one of those computers running non-stop, we still would not get through counting all the possible outcomes of those 266 coin flips. Expand the thought experiment further. 10 billion planets like Earth, each with 10 billion people, each person running a computer checking 10 billion sequences per second, all operating simultaneously across 10 billion parallel universes. Even that staggering, almost comically oversized army of computation would need roughly 100 times the entire age of all of those universes combined just to finish counting. That is the scale of complexity hiding inside something as mundane as a coin. It is a useful reminder that human intuition, built for counting sheep and tracking seasons, was never designed to grasp numbers like these, and that the universe's actual complexity dwarfs almost everything we casually assume to be simple. This is precisely why simulating a molecule can bring a classical supercomputer to its knees. A molecule with only a few dozen atoms already involves an entangled web of quantum interactions among electrons and nuclei, and tracking every possible configuration of that system classically can require more memory and processing time than exists anywhere on the planet. A quantum computer, built from the same underlying rules as the molecule itself, does not need to painstakingly track every configuration one at a time. It can represent the whole tangled mess natively, the same way a native speaker of a language does not need to translate every sentence in their head before understanding it. This is why drug discovery, catalyst design, and materials science keep showing up in every serious conversation about what quantum computers might eventually be good for. Predicting how a new molecule will bind to a protein, or how a new battery material will behave under stress, is exactly the kind of exponentially tangled problem that plays to a quantum machine's strengths. Then there is the problem that made quantum computing famous in the first place, and the reason it worries anyone responsible for digital security, factoring enormous numbers. Most of the encryption protecting online banking, medical records, and private messaging today relies on a system called RSA, named after its 3 inventors. The trick behind RSA is beautifully simple to describe and brutally difficult to break. Multiplying 2 large prime numbers together to get one enormous number takes a computer almost no time at all. Going backward, taking that enormous number and figuring out which 2 primes were multiplied to create it, is a completely different story. There is no known shortcut. A classical computer attempting to factor a sufficiently large number, one with hundreds of digits, would need more time than the current age of the universe, even running continuously on the fastest hardware available today. The largest number of this type ever factored by classical brute force methods to date required roughly the equivalent of 2,000 years of combined computing efforts spread across many machines simultaneously. That gives you a sense of just how lopsided the difficulty really is between multiplying and unmultiplying. This is where a mathematician named Peter Shor changed the conversation entirely. In the 1990s, Shor devised a quantum algorithm capable of factoring large numbers dramatically faster than any known classical method. By exploiting superposition and a mathematical technique related to detecting hidden periodic patterns, a sufficiently large, sufficiently stable quantum computer running Shor's algorithm could, in principle, unravel the exact kind of factoring problem that keeps RSA encryption secure, turning a problem that would take classical machines longer than the universe has existed into something solvable in a matter of hours or less. This single algorithm is the reason governments, banks, and technology companies around the world have begun quietly preparing for what cryptographers call the post-quantum era, developing new encryption methods designed to resist attacks from machines that do not yet exist at the scale required to threaten today's systems, but that many researchers expect eventually will. Encryption is not the only place this kind of advantage shows up. Optimization problems, the sort that involve finding the single best solution among an almost unimaginable number of possibilities, are another natural fit for quantum approaches. Think about routing a fleet of delivery trucks through a city to minimize fuel and time, or coordinating airline schedules across hundreds of routes and gates, or managing the flow of electricity across a power grid with constantly shifting demand. Classical computers handle these problems using approximations and educated shortcuts, because checking every possible arrangement one at a time would take far too long. A quantum computer, capable of representing many candidate solutions simultaneously, has the theoretical potential to zero in on far better answers, far faster, translating directly into savings in fuel, time, and energy at a scale that adds up quickly across an entire economy. None of this means quantum computers are on the verge of replacing the device you are using right now. Here is the part that often gets left out of the more breathless headlines. Quantum computers are, for the overwhelming majority of everyday tasks, dramatically worse than ordinary classical computers, and not just a little worse, but almost comically mismatched for the job. Checking your messages, streaming a video, running the physics engine in a video game. These are deterministic tasks with clear, orderly, step-by-step solutions. Classical processors are exceptionally good at executing long sequences of simple instructions extremely quickly, and there is no advantage to be gained by throwing quantum weirdness at a problem that was never complicated in the first place. Using a quantum computer to check your email would be a bit like chartering a spacecraft to pick up groceries down the street. Technically impressive, wildly impractical, and almost certainly slower once you count the setup time. Even in the domains where quantum computers genuinely shine, they come loaded with practical headaches that classical machines simply do not have. The first is the strange nature of the answer itself. Superposition lets a quantum computer explore many possibilities simultaneously, but the moment you measure the system to get an actual result, that superposition collapses down to a single outcome, and that outcome is inherently probabilistic. Run the exact same calculation twice, and you might get two different answers, each one a valid possible outcome, rather than a guaranteed correct one. To get a reliable result, the same computation often has to be repeated many times, with clever algorithms designed specifically to boost the probability that the correct answer keeps rising to the top. Without that careful engineering, a huge portion of the raw quantum power ends up wasted on statistical noise rather than meaningful output. Then there is the fragility problem, and it might be the single biggest obstacle standing between today's quantum computers and tomorrow's promises. Qubits are extraordinarily delicate. Maintaining a stable quantum state requires shielding it from heat, vibration, stray electromagnetic fields, and practically any interaction with the outside world, because any of these can cause the fragile quantum state to collapse prematurely. a phenomenon researchers call dicoherence. This is why most functioning quantum processors today are kept inside refrigeration systems, cooled to temperatures colder than deep space, just a fraction of a degree above absolute zero, isolated inside layers of shielding designed to keep out even the faintest disturbance. Building and running one of these systems is not just technically difficult, it is enormously expensive. And every additional qubit adds another fragile thread that has to be protected from the slightest disruption. Because qubits are so error-prone, engineers have had to develop elaborate error correction schemes. And this is where the scale of the challenge becomes genuinely staggering. Correcting for the constant small errors that creep into a quantum calculation requires dedicating additional qubits purely to detecting and fixing mistakes, rather than performing useful computation. A problem that might, in a perfect theoretical world, require around 1,000 clean qubits to solve, can realistically require millions of physical qubits, once you account for all the redundancy needed for reliable error correction. Building a machine at that scale is currently far beyond what any laboratory on Earth has achieved. Most of the quantum processors operating today are prototypes working with only a few dozen to a few hundred qubits, nowhere near the millions that would be needed to tackle the largest real-world problems people dream about, like fully breaking modern encryption or perfectly simulating a complex biological molecule. Google's experimental Sycamore processor, for example, has primarily been used to explore fundamental questions in physics and cryptography research rather than to solve commercial problems directly. Rigetti Computing's Aspen series of processors has focused largely on quantum chemistry simulations and accelerating certain machine learning tasks. These systems represent genuinely impressive engineering, but they are still closer to research prototypes than mature industrial tools, and everyone working in the field openly acknowledges that a great deal of progress remains before quantum computing becomes something ordinary businesses can simply plug into their existing workflows. Quantum computers are also, by their very nature, specialists rather than generalists. They are extraordinarily good at a narrow set of problems that align well with the mathematics of superposition and entanglement, factoring large numbers, simulating quantum systems, certain kinds of optimization and search. Outside of that narrow lane, a classical computer will almost always be faster, cheaper, and more practical. There is no such thing as a quantum computer that simply does everything better. What quantum computing offers is not a replacement for classical computing, but a complement to it. A specialized tool reserved for the handful of problems that classical machines were never built to handle in the first place. Despite all these obstacles, progress has not stalled, and one particular announcement in recent years managed to genuinely move the needle. Google introduced a new quantum processor called Willow, built around 105 qubits, and the headline achievement was not simply raw qubit count, but something more fundamental. For the first time, adding more qubits actually reduced the overall error rate of the system rather than making things worse. That distinction matters enormously, because it had long been assumed that scaling up a quantum computer would inevitably make it noisier and less reliable, not more. Willow suggested that a properly engineered error correction architecture could reverse that trend entirely, which is a critical requirement if quantum computers are ever going to scale toward the millions of qubits needed for the largest problems. As a demonstration, Willow completed a specific benchmark calculation in under 5 minutes, a calculation that researchers estimated would take the most powerful classical supercomputers on the planet longer than the current age of the universe to finish through brute force methods. It is worth being precise about what this kind of demonstration does and does not prove. It does not mean Willow can now crack encryption or design new drugs. The specific benchmark task was chosen because it plays directly to a quantum, processes mathematical strengths, and has limited practical application on its own. What it does prove is that the underlying architecture is capable of solving certain classes of problems at a scale that is, for all practical purposes, entirely unreachable by classical brute force, which is exactly the kind of foundational proof of concept the field has needed to justify continued investment and research. At almost the same moment, quantum computing has been grabbing headlines. An entirely different technology has been making its own. Extraordinary claims, artificial intelligence trained on massive datasets. One of the most striking examples came from DeepMind's AlphaFold project, which used machine learning rather than quantum hardware to solve a problem that had stumped biologists for decades, predicting how a protein's chain of amino acids folds into its final three-dimensional shape. That shape determines almost everything about how a protein functions inside a living cell. And getting it wrong by even a small amount can mean the difference between a working treatment and a failed one. AlphaFold's success demonstrated that classical machine learning, given enough data and enough computing power, can sometimes shortcut around problems that seemed, on the surface, to require the kind of exhaustive exploration only a quantum computer could manage. This has led some researchers to argue that certain problems once assumed to require quantum hardware might, in practice, be solvable by sufficiently advanced classical machine learning instead, at least approximately. If that turns out to be broadly true, it would narrow the list of problems where quantum computers offer a genuinely unique advantage. But most people working in both fields tend to push back against framing this as a rivalry. Artificial intelligence and quantum computing are not really competing for the same territory so much as they are exploring overlapping, complementary strengths. Machine learning tends to excel at pattern recognition across huge, messy, real-world datasets, absorbing correlations that are difficult to describe with clean mathematical rules. Quantum computing tends to excel at problems with a precise mathematical structure that happens to mirror the rules of quantum mechanics itself, even when the number of variables involved would overwhelm any classical machine, learning-based or otherwise, rather than one technology making the other obsolete. The more likely future involves hybrid systems that lean on each approach for the parts of a problem it happens to be best suited for. Perhaps the strangest development to come out of quantum computing research so far involves an experiment that had nothing to do with cracking codes or discovering drugs at all. In late 2022, a team of physicists used Google's Sycamore processor to simulate behavior resembling a wormhole, a theoretical tunnel through space-time connecting to distant points. First predicted mathematically by Einstein and his collaborator Nathan Rosen back in the 1930s. To be absolutely clear about what happened and what did not, no actual tunnel through space-time was created. Nothing physically traveled anywhere. What the researchers built was a carefully constructed quantum system whose information dynamics mirrored, mathematically, the predicted behavior of a wormhole according to a specific theoretical framework connecting quantum mechanics to gravity. That framework rests on an idea called the holographic principle, which proposes something genuinely mind-bending, that the complete physical description of a region of space can, at least in certain theoretical models, be encoded entirely on the boundaries surrounding that region. Similar to how a two-dimensional hologram can encode a full three-dimensional image. Building on this, physicist Leonard Susskind and collaborators proposed a conjecture, often summarized with the phrase, Einstein-Rosen bridges equal quantum entanglement, suggesting that wormholes and quantum entanglement might be two different mathematical descriptions of the exact same underlying physical connection. If that conjecture holds up, then entangling two particles is not just correlated behavior, it may be mathematically equivalent, in certain models, to connecting them through a microscopic wormhole. The 2022 experiment worked by encoding entangled quantum states into the processor and manipulating them with an algorithm, specifically designed to mirror this predicted relationship, then observing whether quantum information appeared to travel between the two sides, in a way consistent with the theoretical wormhole. It is worth noting that this experiment sparked real and serious debate within the physics community, not universal celebration. Some researchers pushed back hard on how the result was reported in the media, arguing that headlines describing it as physicists creating a wormhole in a laboratory badly overstated what a small scale, simplified quantum simulation on 9 qubits could actually demonstrate about the vast, complex physics of an actual wormhole predicted by general relativity. Critics were careful to point out that the simulated system was a drastically scaled-down toy model, built specifically to be simple enough for a small quantum processor to handle, and that drawing sweeping conclusions about the nature of real space-time from it required a considerable leap of faith. This kind of internal disagreement is not a weakness in the science. It is exactly how good science is supposed to work, with claims tested, challenged, and refined rather than accepted purely because they sound extraordinary, even accounting for that healthy skepticism. The experiment pointed towards something genuinely interesting. Quantum computers appear to be uniquely suited tools for probing theoretical physics that would otherwise be impossible to test in any laboratory, because they are built from the same fundamental quantum ingredients the theories themselves describe. This has led some physicists toward a much broader and more philosophically loaded idea, one that predates quantum computing but has gained new traction alongside it. The notion that the universe itself might be understood, at some deep level, as an ongoing computation. The physicist Seth Lloyd has argued for a version of this idea for years, suggesting that every interaction between particles, every collision, every exchange of energy, can be thought of as a fundamental computational step, with the entire observable universe amounting to an unimaginably vast quantum computation running itself forward, moment by moment. This is not the same claim as saying we live inside a simulation built by some external programmer, an idea that tends to generate far more headlines than careful physics. It is closer to a proposal about the nature of physical law itself, the idea that information processing might not just describe the universe from the outside, the way a model describes weather, but might actually be what is happening at the most basic level of reality. Physicist John Wheeler captured a similar sentiment decades earlier with his phrase, "it from bit," suggesting that physical reality, at its foundation, might be built from information rather than the other way around. Whether or not this turns out to be a literal description of nature or simply a useful way of framing certain mathematical parallels remains a genuinely open question, and physicists on different sides of the debate hold their positions with real conviction. There is a deeper thread running underneath all of this, one that has less to do with physics and more to do with the way human brains are built. We are drawn, almost instinctively, toward simplicity. When scientists build models of the world, they tend to reach for the simplest version that still fits the data. Not necessarily because nature itself is simple, but because our cognitive machinery is limited in how much complexity it can hold on to at once. Psychologists sometimes describe a related pattern called the streetlight effect, named after the old joke about a man searching for his lost keys under a street lamp, not because he dropped them there, but because that is where the light happens to be. We tend to study the problems we can see clearly, using the tools we already have. and we quietly assume those visible problems represent the whole picture, when in reality they are often just the narrow sliver that happens to be well lit. The 266 coin flip example from earlier is a useful illustration of exactly this bias in action. If someone asked you to predict the outcome of flipping a coin 266 times, the problem would sound almost absurdly difficult given how many possible sequences exist. And yet you could solve it easily in real life, simply by picking up a coin and flipping it, because each flip is independent of the ones before it. You are not tracking billions of possibilities in your head. You are running a simple, repeatable rule over and over, and letting the outcome fall out naturally. The complexity was never really a problem, because the underlying process happened to be simple, even if the space of possible outcomes was enormous. Now imagine a version of that same experiment where each coin flip depends, in some complicated way, on every flip that came before it, the coin effectively carrying a long, tangled memory of its own history. That version of the problem becomes vastly harder, not because there are more possible outcomes, but because there is no simple, repeatable rule left to lean on. This is closer to how real, messy systems in nature actually behave. Whether you are talking about weather patterns, ecosystems, financial markets, or the folding of a complex protein, classical computers, including the most powerful ones ever built, tend to struggle badly with these kinds of deeply interdependent systems. Not because computers are inherently weak, but because we designed them, from the very beginning, to excel at problems with clean, decomposable structure. The computational equivalent of independent coin flips. Quantum computers do not magically escape this limitation either, and this point tends to get lost in more sensational coverage of the field. A quantum computer is not a machine that manages every possible detail of a quantum system without restriction. It is a machine engineered, very deliberately, to solve a specific narrow category of problems that happen to map cleanly onto quantum mathematics, the same way a classical computer is engineered to solve problems that map cleanly onto binary logic. Neither kind of machine eliminates the underlying complexity of the universe. They simply carve out small, solvable corners of that complexity where our tools happen to work, using the resources and understanding currently available to us. The universe's true complexity does not shrink just because we have found a clever new way to work around a small piece of it. This matters because it reframes what a phrase like quantum advantage actually means. It does not mean quantum computers have surpassed classical computers everywhere, or that they never will need classical computers alongside them. It means that, for a specific category of problems, a quantum machine can do something a classical machine effectively cannot do at all within any reasonable amount of time. Not that quantum machines have become the superior choice across every category of computation. The distinction sounds subtle, but it changes the entire tone of the conversation, shifting it from a story about one technology replacing another to a story about expanding the total range of problems humanity is equipped to tackle. It is worth pausing on the word measurement, because it hides one of the deepest unresolved puzzles in all of physics, one that quantum computing brings into sharp practical focus rather than resolution. Before a qubit is measured, it exists in superposition, a combination of possible states. The instant it is measured, that superposition appears to collapse into one single, definite outcome. What actually happens during that collapse, physically and philosophically, remains genuinely unsettled more than a century after quantum mechanics was first developed. The most widely taught explanation, often called the Copenhagen interpretation, essentially treats the act of measurement as a fundamental part of the theory, without dwelling too deeply on what measurement really means at a physical level, or why it produces a single outcome rather than several. Generations of physics students have been taught to accept this and move on, largely because the mathematics works extraordinarily well at predicting experimental results. Even if the underlying story feels incomplete, an alternative view, known as the many worlds interpretation, proposes something far stranger, that superposition never actually collapses at all. Instead, every possible outcome continues to exist, just in separate, non-interacting branches of reality that split apart at the moment of measurement. On this view, there is no version of you that sees the coin land on tails and a lucky winner who saw heads. There are simply two separate branches of the universe, one in which you observed tails and one in which a version of you observed heads, with neither branch aware of the other. This interpretation avoids the awkward question of why superposition collapses, because in this picture it never does. But it comes at the cost of accepting an almost incomprehensibly vast multiplication of parallel realities, branching apart with every quantum event happening anywhere in the universe. At every moment, there are other interpretations as well, involving hidden variables, or objective spontaneous collapse mechanisms built directly into the equations, or frameworks that treat probability itself as something more fundamental than we usually assume. None of these interpretations currently has a decisive experimental advantage over the others. They all make essentially the same predictions for any experiment physicists know how to actually perform today, which is precisely why the debate has persisted for so long without resolution. Quantum computers do not settle this argument, but they do force engineers to grapple with it in an unusually direct, practical way, because building a machine that depends on maintaining and later collapsing superposition means constantly running into the exact philosophical fault line that theoretical physicists have been arguing about since the earliest days of the field. Setting the interpretation debate aside, the engineering side of quantum computing has been advancing along several genuinely different hardware paths, each with its own trade-offs. And understanding this diversity matters if you want to follow the field honestly rather than through a single company's headline announcements. Superconducting qubits, the type used in Google's Sycamore and Willow processors along with IBM's quantum systems, rely on tiny circuits cooled to temperatures near absolute zero, where electrical current can flow with essentially no resistance and behave according to quantum rules. This approach has produced some of the largest qubit counts to date, but it demands extremely elaborate cooling infrastructure and remains highly sensitive to any stray interference. A separate approach uses trapped ions, individual charged atoms suspended and manipulated using precisely tuned laser light. Trapped ion qubits tend to hold their quantum states for longer periods and suffer from fewer errors compared to some superconducting designs, though scaling up to very large numbers of ions, while keeping them all precisely controlled, introduces its own engineering headaches. Photonic quantum computing takes yet another route, encoding information directly into particles of light, which has the appeal of potentially operating at room temperature rather than requiring extreme refrigeration. Since photons do not interact strongly with their surroundings the way charged particles do, neutral atom platforms, which use arrays of individual atoms held in place with tightly focused laser beams, have also gained serious traction recently as a promising middle path, offering a route toward large qubit counts without some of the extreme cooling demands of superconducting circuits. Meanwhile, a more experimental approach pursued by researchers at Microsoft and elsewhere aims to build what are called topological qubits, which would theoretically be far more naturally resistant to the kinds of errors that plague other qubit types. Though building a stable, working version of this technology has proven to be an extraordinarily difficult engineering challenge, with progress claims in this specific area facing unusually intense scientific scrutiny over the years. Shor's factoring algorithm tends to dominate the headlines because of its direct relevance to encryption, but it is far from the only quantum algorithm worth knowing about. Another landmark algorithm, developed by the computer scientist Loaf Grover, tackles a different but equally common problem, searching through an enormous unsorted list to find a specific item. Classically, if you have no shortcuts and no way to sort the list in advance, finding a particular entry among a huge number of possibilities requires checking, on average, about half of all the entries before you get lucky. Grover's algorithm allows a quantum computer to find that entry using roughly the square root of the number of steps a classical search would need. That might sound like a modest improvement compared to the explosive speed-up offered by Shor's algorithm, but for sufficiently large search spaces, a square root reduction in required steps still represents an enormous practical advantage. And, unlike factoring, unstructured search shows up constantly across countless real-world computing problems, from database queries to optimization tasks. Beyond these two landmark algorithms, researchers have also developed a category of approaches known as variational quantum algorithms, designed specifically to work on the smaller, noisier quantum processors available today, rather than waiting for some distant future machine with millions of perfectly error-corrected qubits. These variational methods combine a quantum processor with a classical computer working alongside it in a feedback loop, using the quantum hardware to explore certain calculations, while a classical algorithm continually adjusts the approach based on the results, gradually converging toward a useful answer even without perfect, fully fault-tolerant qubits. This hybrid strategy is part of why so much current quantum computing research focuses on chemistry and materials science applications specifically, since these problems tend to tolerate the kind of approximate, iterative approach that variational algorithms offer, even on today's imperfect, error-prone hardware. The looming threat that Shor's algorithm poses to modern encryption has already triggered a real, ongoing response from the cybersecurity world, well before any quantum computer capable of actually running the algorithm at a meaningful scale exists. The United States National Institute of Standards and Technology, along with similar bodies in other countries, has spent years running a formal, public process to select new encryption standards specifically designed to resist attacks from a future quantum computer, an effort generally referred to as post-quantum cryptography. Most of the leading candidates rely on mathematical problems involving complex geometric structures called lattice, problems that, as far as anyone currently knows, remain difficult even for a quantum computer to solve efficiently. Unlike the factoring problem that Shor's algorithm was specifically designed to crack, several major technology companies and government agencies have already begun the slow, deliberate process of migrating their systems toward these new quantum-resistant standards, not because a code-breaking quantum computer exists today, but because sensitive data encrypted now could potentially be intercepted, stored, and decrypted years or even decades later once sufficiently powerful hardware finally arrives. A strategy security researchers sometimes describe using the phrase "harvest now, decrypt later." This raises a natural question worth addressing directly. How close are we, really, to a quantum computer capable of breaking encryption at scale? The honest answer is that estimates vary considerably depending on who you ask, and the field has already been burned once by overly confident headlines. Back in 2019, Google published research claiming to have achieved what researchers called quantum supremacy, demonstrating a specific calculation that their quantum processor completed in roughly 200 seconds. a calculation the team estimated would take the world's most powerful classical supercomputer, at the time approximately 10,000 years, to replicate. IBM, a major competitor in the space, publicly pushed back almost immediately, arguing that with sufficiently clever classical algorithms and enough conventional supercomputing resources, the same calculation could actually be completed in a matter of days rather than millennia, a dramatically smaller gap than Google's original claim suggested. This back and forth highlights something important about how these milestones should be read. The exact size of any quantum advantage tends to shrink somewhat once classical researchers get a chance to respond with improved algorithms of their own, and each side has strong incentives to describe the results in the most favorable light for their own approach. None of this means the underlying quantum hardware achievements were fake or unimportant, but it does mean that treating any single headline as the final word on the state of the field is a mistake worth avoiding. Zoom out far enough, and the story of quantum computing looks less like a single breakthrough and more like a decades-long relay race, with different researchers, companies, and countries each carrying the idea a little further before handing it off. Feynman's original suggestion in the early 1980s sat largely as an academic curiosity for years, discussed mostly among theoretical physicists rather than engineers. Real experimental progress did not begin accelerating until the 1990s and 2000s, as researchers slowly learned how to isolate, control, and read out individual quantum systems reliably enough to build even the smallest functional prototypes. Early demonstrations involved just a handful of qubits, capable of performing only the most basic proof of concept calculations, nowhere close to solving any problem a classical computer could not already handle more easily. The pace changed noticeably over the past decade, as private investment and national research funding both poured into the field at a scale that would have seemed unthinkable to the field's founders. Major technology companies each staked out their own hardware approach and invested heavily in scaling it, alongside a growing number of dedicated quantum computing startups, pursuing everything from superconducting circuits to trapped ions to photonic systems. Government-backed national initiatives in the United States, the European Union, China, and elsewhere have committed substantial long-term funding toward quantum research, treating the technology as a strategic priority comparable to how earlier generations treated space exploration or early computing itself. China, in particular, has invested heavily in both quantum computing and quantum communication infrastructure, including satellite-based quantum key distribution experiments designed to test secure communication across genuinely vast distances, extending the same basic photon-based principles discussed earlier in this very explanation, just scaled up from a laboratory bench to orbit. Despite all this investment, nearly everyone working seriously in the field, rather than merely promoting it, tends to agree on a fairly sober timeline. Building a large-scale, fully fault-tolerant quantum computer capable of running Shor's algorithm against the encryption standards used today would likely require millions of stable, error-corrected logical qubits, translating into a physical qubit count potentially in the range of tens of millions. Once you account for the overhead of error correction schemes, current state-of-the-art processors operate with qubit counts in the hundreds, not the millions, meaning there remains a gap of several orders of magnitude between today's most advanced hardware and the scale genuinely needed to threaten modern cryptography directly. Estimates for when that gap might close vary widely, from a decade or so on the more optimistic end, to several decades or more on the more cautious end. And it is worth being honest that predictions in this specific area have a long history of being wrong in both directions, sometimes too optimistic and occasionally too conservative, as unexpected engineering breakthroughs have periodically compressed timelines that once seemed fixed. Part of what makes forecasting so difficult is a concept from theoretical computer science called the threshold theorem, which describes a critical tipping point in quantum error correction. Below a certain error rate per physical qubit, adding more qubits to a fault-tolerant design actually makes the overall system more reliable, because the error correction scheme can outpace the rate at which mistakes accumulate. Above that threshold, adding more qubits instead makes things worse, because errors compound faster than the correction scheme can fix them. Google's Willow demonstration mattered so much specifically because it offered strong evidence that a particular error correction architecture, based on something researchers call a surface code, had crossed below that critical threshold, meaning that scaling the system up further should, in principle, continue improving reliability rather than degrading it. Crossing that threshold does not instantly deliver a machine capable of breaking encryption, but it removes one of the most fundamental theoretical obstacles standing in the way, shifting the remaining challenge toward pure engineering scale rather than an open question about whether the underlying physics would even cooperate. The wormhole simulation experiment mentioned earlier connects to an even older and more famous puzzle in physics, one that has occupied some of the field's sharpest minds for half a century: the black hole information paradox. According to quantum mechanics, information about a physical system should never be truly destroyed, only scrambled into a form that is difficult to read but never permanently erased. According to the classical picture of black holes developed from general relativity, anything that falls past the event horizon seems to be lost forever, with the black hole eventually evaporating away entirely through a slow process known as Hawking radiation, named after physicist Stephen Hawking, who first predicted it. If the black hole eventually vanishes completely, and the information that fell into it never comes back out in any recoverable form, then information appears to have been destroyed, directly contradicting one of the core assumptions of quantum theory. This contradiction, seemingly small on the surface, strikes at the heart of how well physicists actually understand the relationship between gravity and quantum mechanics, two theories that work extraordinarily well individually, but have resisted every serious attempt to merge them into a single unified framework: the holographic principle and the broader theoretical framework built around it, often called the anti-de Sitter space and conformal field theory correspondence, offers one of the more promising paths toward resolving this paradox, at least within certain simplified theoretical models. The core idea proposes a mathematical equivalence between a theory of gravity operating inside a particular curved region of space and a completely separate quantum theory without gravity at all, operating on the boundary surrounding that region. If these two descriptions really are mathematically equivalent, as the framework suggests, then whatever happens to information falling into a black hole in the gravitational picture should have some corresponding, fully quantum mechanical description on the boundary, one where information loss is explicitly forbidden by the rules of quantum theory. This would mean the information is not actually destroyed inside the black hole at all, but merely encoded in an extraordinarily scrambled, difficult to reconstruct form, something closer to a complicated puzzle than genuine annihilation. This is precisely why quantum computers have become such compelling tools for exploring this kind of theoretical physics directly, rather than only through pen and paper mathematics. A quantum processor built from the same fundamental quantum ingredients that the theory itself describes offers physicists a rare opportunity to construct small, simplified, laboratory-scale versions of these exotic theoretical scenarios and actually observe how they behave. Rather than relying purely on abstract calculation, The 2022 wormhole simulation was, in this sense, less about proving anything definitive about the nature of black holes, and more about demonstrating that quantum hardware had finally reached a point where it could begin acting as a genuine experimental testbed for ideas that had previously existed only within the realm of theoretical speculation. Even with all the caveats and legitimate scientific pushback the experiment received, that shift alone, from pure theory to something at least partially testable, represents real, meaningful progress, and it is a trend many physicists expect to continue as quantum hardware slowly scales up over the coming years, stepping back from the deepest theoretical corners of the field. It is worth returning to why any of this matters beyond academic curiosity, because the practical applications, while less headline-grabbing than wormholes and encryption, are where quantum computing is actually expected to leave its earliest fingerprints on ordinary life. Drug discovery is a good place to start, because the process of developing a new medication today is astonishingly slow and expensive, often taking more than a decade and costing well over 1 billion units of currency by the time a single successful drug reaches the market, with the overwhelming majority of candidate compounds failing somewhere along the way. A significant portion of that cost comes from the sheer difficulty of predicting in advance how a candidate molecule will actually behave once it interacts with a target protein inside the human body. Classical simulation methods rely heavily on approximations, because fully modeling every quantum interaction between every atom in a reasonably sized molecule is simply beyond what classical computers can handle in any practical amount of time. A sufficiently capable quantum computer, simulating these interactions using the same underlying quantum rules the molecules themselves obey, could in principle model this chemistry with far greater accuracy, potentially cutting years off the discovery timeline and helping researchers rule out failing candidates far earlier in the process, before enormous amounts of money and laboratory time have already been invested. Materials science offers a similarly compelling case. The search for better battery materials, for example, one of the central bottlenecks holding back cleaner energy storage and electric transportation, depends heavily on understanding exactly how lithium ions and other charged particles move through candidate materials at the atomic scale. Small changes in atomic structure can produce dramatic differences in a battery's capacity, charging speed, and long-term stability, and predicting those differences accurately currently requires either expensive, time-consuming laboratory experimentation or heavily simplified computer models that only approximate the real underlying physics. Quantum simulation offers a path toward modeling these material properties directly and accurately, potentially accelerating the search for better batteries, more efficient solar cells, and stronger, lighter structural materials, all of which carry meaningful consequences for how quickly the world can transition toward cleaner energy infrastructure, even weather and climate modeling. An area often assumed to be purely a classical supercomputing problem, has attracted growing interest from quantum researchers, though this remains one of the more speculative applications under active investigation, where the systems are governed by fluid dynamics, equations that become extraordinarily difficult to solve, precisely once you account for the full complexity of a real atmosphere, with countless interacting variables across enormous ranges of scale, from microscopic droplet formation up to continent-spanning pressure systems. While quantum computers are unlikely to replace the massive classical supercomputing infrastructure currently used for weather forecasting anytime soon, some researchers are exploring whether quantum algorithms could eventually assist with narrow, well-defined pieces of the overall modeling problem, particularly around simulating certain kinds of turbulent fluid behavior that classical methods still struggle to capture efficiently. Financial modeling represents another frequently discussed application, particularly around portfolio optimization and risk analysis. Problems that often involve searching through an enormous number of possible combinations to find an optimal or near-optimal solution under a set of real-world constraints. Several major financial institutions have already begun experimenting with early-stage quantum algorithms for exactly this kind of optimization work, treating current prototype hardware less as a production-ready tool and more as an early investment in expertise and infrastructure, positioning themselves to take fuller advantage once the underlying hardware matures enough to deliver a clear, reliable, practical advantage over existing classical methods. It is tempting, after walking through all of this, to file quantum computing away as simply the next chapter in the long history of faster and more powerful machines. An upgrade in the same lineage as moving from vacuum tubes to transistors to modern microchips. That framing misses something important, though, and it is worth spelling out clearly. Every previous leap in classical computing, no matter how dramatic, still operated according to the same basic binary logic, zeros and ones flipping through circuits in sequence. Quantum computing represents something categorically different, not a faster version of the same idea, but a machine built on an entirely separate set of physical rules. Rules that describe reality at its most fundamental level in a way that has never made intuitive sense to human beings. And that, arguably, still does not, even to the physicists who understand the mathematics best. Building a working computer out of those rules means engineering has finally caught up to a layer of physical reality that, until recently, existed only as abstract theory confirmed through delicate laboratory experiments, never as something you could point to inside a functioning machine designed to solve a chosen problem on demand. That is also precisely why so many open questions remain. And honest scientific communication requires being upfront about them rather than glossing over the uncertainty. Nobody currently knows, with confidence, exactly when a quantum computer capable of breaking today's strongest encryption standards will actually exist. Only that current progress suggests it is a matter of continued engineering effort rather than some undiscovered law of physics standing permanently in the way. Nobody knows for certain whether topological qubits, the more exotic and theoretically more error-resistant approach some researchers are pursuing, will ever be stabilized reliably enough to become a mainstream technology, or whether that particular path will end up being a historical dead end that other, less elegant approaches simply outpaced through brute force engineering. Nobody knows whether the deep philosophical questions surrounding quantum measurement, superposition, and the true nature of wave function collapse will ever be resolved experimentally, or whether they will remain permanently locked behind a wall of mathematically equivalent interpretations that make identical predictions but tell fundamentally different stories about what is actually happening, and nobody knows with any real certainty whether ideas like the universe operating as a fundamental quantum computation represent a genuinely deep truth about physical reality, or simply a compelling metaphor that happens to describe certain mathematical parallels usefully without corresponding to anything literally true about how existence actually works underneath the surface. These are not failures of the field. They are honest markers of where current human understanding runs out. The edge of the map where genuine research is still actively being done rather than simply reported after the fact. Some of the smartest people alive are actively working on exactly these questions right now, in laboratories and universities scattered across the globe, running experiments specifically designed to chip away at these uncertainties one careful measurement at a time. What continues to make this field worth paying attention to is not any single breakthrough, dramatic as some of them have genuinely been. But the fact that it sits at a rare intersection where practical engineering, foundational physics, and deep philosophical questions about the nature of reality all collide simultaneously. Very few areas of active research can claim that their next incremental hardware improvement might simultaneously bring humanity closer to curing a disease, threaten the security infrastructure protecting the entire internet, and offer new experimental evidence relevant to century-old debates about the fundamental structure of physical reality itself. That combination is rare, and it is a large part of why researchers across wildly different specialties, from cryptographers to biochemists to theoretical physicists studying black holes, all find themselves paying close attention to the same experimental hardware for entirely different reasons. It is worth pausing to underline that entanglement itself, the property doing so much of the heavy lifting throughout everything discussed so far, is not merely a convenient theoretical assumption borrowed for the sake of building computers. It has been tested directly, repeatedly, and rigorously in laboratories for decades, through a category of experiments known as Bell tests, named after physicist John Bell, who devised a mathematical framework in the 1960s for distinguishing genuine quantum entanglement from any possible classical explanation involving hidden, unmeasured properties shared between particles in advance. Physicist John Clauser, Elling Aspect, and Anton Zeilinger were jointly awarded the Nobel Prize in Physics in 2022, specifically for their pioneering experimental work, confirming with extraordinary precision that entanglement behaves exactly as quantum mechanics predicts, definitively ruling out an entire broad category of classical explanations that some physicists, Einstein among them, had once hoped might restore a more intuitive, common-sense picture underneath the strangeness. That prize represents decades of increasingly careful, increasingly loophole-free experimentation, closing off one potential escape route after another, until the conclusion became essentially unavoidable. Entanglement is not a mathematical trick or a statistical illusion. It is a genuine feature of how the physical world actually operates. However uncomfortable that conclusion remains for human intuition built around a much more classical, locally connected picture of reality, this experimentally confirmed weirdness has already begun spawning practical technology well beyond computation and cryptography, in a growing field sometimes called quantum sensing, because quantum systems are so exquisitely sensitive to their survival, a property that causes so many headaches for quantum computing engineers trying to prevent decoherence. That very same sensitivity can be turned into an advantage when the goal is detecting subtle physical signals, rather than performing stable calculations. Atomic clocks, which already rely on the precise quantum mechanical vibration frequencies of individual atoms, represents some of the most accurate timekeeping devices ever built. Accurate enough that they would neither gain nor lose a single second over timescales far longer than the current age of the universe. Researchers are also developing quantum sensors capable of detecting minuscule variations in gravity or magnetic fields. Technology with potential applications ranging from detecting underground mineral deposits and monitoring volcanic activity, to potentially improving navigation systems that do not rely on satellite signals at all. An area of particular interest for submarines and other applications, where satellite-based positioning is unavailable or unreliable. A related emerging area, often called the quantum internet, aims to extend entanglement-based communication well beyond the single laboratory-scale demonstrations discussed earlier, toward a genuine network capable of distributing entangled particles across long distances reliably. Building this kind of network requires solving a stubborn, technical problem, Entangled photons traveling through fiber optic cables gradually lose their delicate quantum properties over distance, the same fragility that plagues quantum computers in general. Researchers are actively developing devices called quantum repeaters, designed to extend the effective range of entanglement distribution without directly measuring, and therefore destroying the fragile quantum states passing through them. China has already demonstrated entanglement distribution across genuinely vast distances using a dedicated quantum communication satellite, successfully sharing entangled photon pairs between ground stations separated by well over 1,000 kilometers, a feat that would have sounded like clear science fiction only a few decades earlier, when Bennett and Brassard first proposed the theoretical foundation for quantum key distribution back in 1984. It is fair to ask, at this point, why any of this feels so deeply unintuitive in the first place, given how thoroughly confirmed it all is through repeated experimentation. Part of the answer lies in a simple, almost mundane fact about biology. Human brains evolved to track medium-sized objects moving at medium speeds across a world governed overwhelmingly by classical physics. Catching thrown spears, judging the trajectory of a falling branch, predicting where a running animal will end up next. None of that evolutionary pressure ever required an intuitive grasp of how a single electron behaves, because at the scale humans actually operate in, quantum effects average out almost completely, disappearing into the smooth, predictable, classical behavior we experience every day. This transition from strange quantum behavior at the smaller scales to familiar classical behavior at the scales we actually live in is itself an active area of physics research, generally explained through a process called decoherence, in which a quantum system's delicate superposition gets rapidly and irreversibly scrambled through countless unavoidable interactions with its surrounding environment, effectively washing out the quantum weirdness and leaving behind the ordinary, classical world familiar from everyday experience. This is also why a phenomenon like the classic double-slit experiment tends to strike people as so unsettling the first time they encounter it. In its simplest form, individual particles, whether photons of light or even larger particles like electrons, are fired one at a time toward a barrier containing two narrow slits, with a detector screen positioned behind it to record where each particle lands. If you could somehow track which slit each individual particle passed through, the particles behave exactly as you would classically expect, piling up into two distinct clusters directly behind each slit. But if you do not track which slit each particle passes through, allowing the possibility to remain genuinely open and unmeasured, an interference pattern gradually emerges across the detector screen instead. The same kind of pattern you would expect from overlapping waves, not discrete particles. Each individual particle appears to behave as though it explored both possible paths simultaneously, only settling into a single definite trajectory once a measurement forces the issue. This single experiment, repeated countless times with steadily improving equipment since it was first performed in a simplified form in the early 1800s, and then radically extended throughout the 20th century, captures the essential strangeness that superposition, entanglement, and everything discussed throughout this explanation ultimately traces back to quantum computing in a very real sense, is simply the engineering discipline that emerged from taking this strangeness seriously enough to build something useful out of it, rather than treating it as a curious footnote confined to physics. Lectures, if any part of this has left you, rethinking how confidently you can trust your own intuition about how reality actually works at its smallest scales. You are reacting exactly the way many professional physicists have reacted throughout the history of this field, and that reaction is a genuinely reasonable one to have. If you found this kind of explanation useful, sharing it with someone who has heard the phrase quantum computer thrown around without ever getting a clear sense of what that actually means is a good way to spread a slightly more accurate picture of the field. And taking a moment to like this video or subscribe for more explanations, like it helps this kind of careful, grounded science communication keep reaching more people who are curious about exactly these kinds of questions. Looking ahead, the milestones researchers themselves are watching most closely are less about splashy public demonstrations and more about steady, incremental progress toward fault tolerance. The point at which a quantum computer can run arbitrarily long calculations without errors accumulating faster than they can be corrected. IBM has published a public roadmap outlining planned increases in qubit count alongside improvements in error rates, aiming toward what the company describes as genuinely useful, fault-tolerant quantum computing within the next decade. Though roadmaps of this kind should always be read as ambitious targets rather than guaranteed outcomes, given how frequently timelines in this field have shifted in both directions as new engineering challenges emerge. Other companies pursuing trapped ion and neutral atom approaches have published their own competing timelines, each betting that their particular hardware platform will scale more gracefully than the alternatives once the engineering challenges of maintaining larger numbers of stable, well-controlled qubits are fully worked out. One particularly important milestone researchers watch closely is the demonstration of a genuinely useful logical qubit, a single unit of stable, error-corrected quantum information built from a larger cluster of noisy, physical qubits working together through an error correction code. Google's Willow processor, along with competing efforts at other companies, has already demonstrated logical qubits with error rates lower than the physical qubits used to build them, an important proof that the error correction architecture itself is working as theoretically predicted. The next major milestone the field is watching for involves scaling this same approach up to dozens, then hundreds, then eventually millions of logical qubits working together reliably, at which point encryption-breaking algorithms like Shor's method would move from theoretical possibility to genuine practical threat. Nobody currently expects that particular milestone within the next few years, but few researchers in the field would confidently rule it out within the coming few decades either, which is precisely why post-quantum cryptography migration efforts, discussed earlier, continue moving forward steadily rather than waiting for a more definitive deadline to materialize. Bringing all of this back to where the explanation began. The reason a lock protecting your data today could plausibly be picked by a machine that does not yet fully exist is not science, fiction speculation. It is a direct, well-understood mathematical consequence of Shor's algorithm combined with a genuinely difficult, but not physically impossible, engineering challenge that thousands of researchers around the world are actively working to solve, one carefully measured qubit at a time. Nothing about that story requires exaggeration, dramatic framing, or manufactured mystery to be worth paying attention to. The mathematics of superposition and entanglement, confirmed through decades of increasingly rigorous experimentation, already provides more than enough genuine strangeness on its own, without needing any embellishment. What remains unknown is not whether quantum mechanics is real. That question was settled through Bell test experiments and a Nobel Prize awarded specifically for closing off the last remaining classical explanations. What remains genuinely open is how quickly engineering can catch up to theory, whether the deepest philosophical questions about measurement and reality will ever find experimental resolution, and whether ideas connecting quantum information to the fundamental structure of space-time itself, hinted at by experiments like the 2022 wormhole simulation, represent a glimpse of something genuinely profound about the universe, or simply a compelling mathematical analogy that happens to describe certain patterns usefully. Research continues on every one of these fronts simultaneously in laboratories that are, in a very real sense, trying to build small, carefully controlled pockets of the same strange rules that govern everything else in existence, one stable qubit at a time, in the hope of eventually understanding not just how to compute faster, but how reality itself actually works underneath the surface. We happen to be able to see that there is one more thread worth pulling on before closing, because it reframes the entire subject in a way that is easy to miss once you have absorbed all the individual technical pieces. Every technology discussed throughout this explanation, from quantum key distribution to Shor's algorithm to the wormhole simulation, ultimately traces back to the exact same handful of physical properties: superposition, entanglement, and the strange, still not fully understood process by which measurement collapses possibility into a single observed outcome. That is a remarkably small set of underlying ingredients to produce such a wide, almost bewildering variety of applications and open questions. A shift in perspective as simple as taking these properties seriously enough to engineer around them, rather than dismissing them as strange footnotes confined to physics classrooms, has already produced secure communication systems immune to computational attack. Algorithms capable of threatening the entire foundation of modern internet security. Small-scale physical models of theoretical wormhole, and increasingly precise sensors capable of detecting signals no classical instrument could ever hope to measure. That breadth is exactly why quantum computing tends to resist easy categorization as belonging to any single field. It sits simultaneously inside computer science departments, physics departments, chemistry laboratories, and cybersecurity agencies, each approaching the same underlying phenomena from a completely different angle, chasing different goals, but ultimately drawing from the identical well of strange quantum behavior first hinted at by Schrödinger's equation nearly a century ago. Very few scientific developments managed to remain relevant across such a wide span of disciplines for this long without becoming outdated or narrowly specialized. And that persistent relevance is a strong signal that there is still a great deal of genuine substance left to uncover, rather than a topic that has already been thoroughly mined and mostly explained. None of this requires exaggerating what has already been achieved, or manufacturing artificial suspense about what comes next. The honest version of the story is compelling enough entirely on its own. A century ago, a strange equation describing probabilities rather than certainties reshaped how physicists understood the smallest building blocks of reality. Half a century after that, a handful of researchers began wondering whether those same strange rules could be harnessed rather than merely observed. And within the past 2 decades, that wondering has produced working hardware, real-world cryptographic infrastructure, and genuine experimental glimpses into some of the deepest unresolved questions physics has ever asked. Wherever this research leads over the coming years, whether toward a machine capable of reshaping cybersecurity as we know it, toward new medicines and materials discovered through simulation rather than trial and error, or toward a deeper understanding of how information, gravity, and the fabric of space-time itself might ultimately be connected, it is a story built entirely on real, tested, repeatedly confirmed science, and that, on its own, is more than enough reason to keep watching closely, to fully appreciate how strange all of this once seemed, and in many ways still seems. It helps to look back at how quantum mechanics was originally received by the very physicists who developed it. Albert Einstein, despite having contributed some of the foundational insights that helped launch quantum theory in the first place, spent much of his later career deeply uncomfortable with where the theory ultimately led. Alongside physicists Boris Podolsky and Nathan Rosen, Einstein published a paper in 1935 specifically designed to expose what he saw as a fatal flaw in quantum mechanics, arguing that entanglement implied either an impossible faster-than-light influence between distant particles or the existence of hidden properties the theory failed to account for. Einstein favored the second explanation, famously insisting that a complete physical theory should not require what he dismissively called spooky action at a distance. Niels Bohr, one of the primary architects of the standard interpretation of quantum theory, pushed back forcefully, arguing that Einstein's thought experiment, while cleverly constructed, did not actually reveal a flaw in the theory itself, but rather a mismatch between quantum reality and the classical intuitions Einstein was still implicitly relying on. This disagreement between two of the most brilliant physicists of the 20th century remained unresolved through experiment for nearly 3 decades, existing purely as a philosophical dispute about interpretation, until John Bell devised his mathematical test in the 1960s, finally providing a way to settle the question empirically rather than through debate alone. When those experiments were finally run with sufficient precision, decades later, the results came down firmly on Bohr's side, not Einstein's, confirming that no hidden classical properties could explain the correlations observed between entangled particles. Einstein, for all his genius, turned out to be wrong about this particular question, a humbling reminder that even the most celebrated scientific minds in history can hold deeply mistaken intuitions about how nature actually behaves, particularly when that behavior departs so radically from anything encountered in ordinary experience. It is a useful historical footnote to keep in mind whenever quantum mechanics still feels personally unconvincing or uncomfortable, because it clearly was for Einstein too. And being uncomfortable with an idea has never been the same thing as that idea being false. There is also a formal, mathematical way of describing exactly how much of an advantage quantum computers offer, beyond the more intuitive explanations already covered, and it comes from an area of computer science called computational complexity theory. Researchers in this field classify problems according to how the resources required to solve them scale as the problem grows larger. Quantum computers are associated with their own particular complexity class, generally referred to using the shorthand phrase bounded error quantum polynomial time, which describes the set of problems a quantum computer can solve efficiently, with a high probability of correctness within a reasonable amount of time. A significant portion of ongoing theoretical computer science research involves carefully mapping out exactly how this quantum complexity class relates to the more familiar classical complexity classes that describe problems solvable efficiently by ordinary computers, and problems believed to require exponentially more time no matter how they are approached. This remains an active area of open mathematical research, not fully settled science, and part of what makes it so interesting is that proving certain relationships between these complexity classes with full mathematical rigor has turned out to be almost as difficult as some of the underlying computational problems themselves, a rare case where the theory describing the limits of computation is itself pushing right up against the practical limits of what current mathematical tools can prove, bringing the discussion back down from abstract complexity theory to concrete chemistry. One specific example illustrates just how much practical value might be waiting inside a sufficiently powerful quantum simulation. Consider the industrial process used to produce ammonia, a compound essential to manufacturing the fertilizer that feeds a substantial portion of the world's population. the standard industrial method for producing ammonia, developed over a century ago and still relied upon today, requires extremely high pressure and high temperature conditions, consuming an enormous amount of energy in the process, purportedly responsible for a noticeable percentage of global energy consumption on its own. Certain bacteria, by contrast, are able to accomplish the exact same chemical transformation at ordinary room temperature and pressure, using a specialized enzyme containing a cluster of iron and molybdenum, atoms that current computational chemistry methods still cannot fully simulate with confidence, because the electronic interactions within that metal cluster are simply too complex for classical computers to model precisely. If a sufficiently capable quantum computer could finally simulate that enzyme's electronic structure accurately, researchers might be able to design an artificial catalyst capable of replicating nature's remarkably efficient trick, potentially eliminating a meaningful slice of global industrial energy consumption in the process. This single example captures why quantum chemistry simulation, despite sounding abstract and academic, could carry consequences reaching directly into agriculture, energy policy, and climate impact, all stemming from finally being able to accurately model something as small and specific as a single metal cluster embedded inside a bacterial enzyme. Similar reasoning applies to the decades-long search for materials capable of conducting electricity with zero resistance at everyday, easily achievable temperatures, rather than requiring the extreme cooling currently needed for known superconducting materials. A material like that, sometimes described as a room temperature superconductor, could transform electrical power transmission by eliminating the energy losses that currently occur whenever electricity travels through ordinary wires and cables. Losses that add up to a significant amount of wasted energy across any large-scale power grid. Predicting in advance which combinations of elements and crystal structures might produce this kind of behavior requires accurately simulating how electrons interact and pair up within a material's atomic lattice, precisely the kind of deeply interconnected quantum problem that classical computers handle only through rough approximation. Several research groups working on quantum simulation have specifically identified superconductivity research as one of the more promising near to medium-term applications for quantum hardware, not because a breakthrough is guaranteed, but because the nature of the problem aligns so closely with what quantum computers are. Fundamental, grounded examples matter because they anchor an otherwise abstract and sometimes overhyped field to specific, testable, real-world stakes. It is one thing to say a quantum computer might someday help discover new materials in the abstract. It is another to point directly at a specific, well-understood industrial process. Note precisely where classical simulation methods currently fail, and explain exactly why a quantum approach could plausibly succeed where those classical methods cannot. That kind of specificity is exactly what separates careful, grounded science communication from speculative hype. And it is worth holding on to that distinction whenever quantum computing comes up in casual conversation or online discussion, because the gap between what has actually been demonstrated and what remains genuinely speculative is often far larger than headlines tend to suggest. In either direction, one more emerging thread deserves mention before wrapping up, because it sits directly at the overlap between the two technologies discussed earlier as complementary rather than competing. Quantum machine learning. Researchers have begun exploring whether certain machine learning tasks, particularly those involving recognizing patterns within highly complex, high-dimensional data, might benefit from being run partly on quantum hardware rather than entirely on classical processors. The theoretical appeal is straightforward enough. Superposition allows a quantum system to represent an enormous number of data points simultaneously, and some researchers have proposed that certain classification and pattern recognition tasks could, in principle, be accelerated by encoding data into quantum states and processing it using specifically designed quantum algorithms. In practice, this remains one of the more contested corners of the field. Early enthusiasm for quantum machine learning has been tempered somewhat by a series of papers demonstrating that several proposed quantum speedups could actually be matched, or nearly matched, by sufficiently clever classical algorithms once researchers looked closely enough, echoing the same pattern seen earlier with artificial intelligence encroaching on territory once assumed to require quantum hardware exclusively. This does not mean quantum machine learning is a dead end, but it does mean that claims in this particular corner of the field deserve an extra measure of scrutiny, since the history of the subfield already includes several instances of an apparent quantum advantage quietly evaporating once classical researchers were given a fair chance to respond with improved techniques of their own. Some of the more durable proposed advantages involve using small quantum processors to generate specific kinds of complex probability distributions that would be genuinely difficult for a classical computer to produce efficiently. Distributions that could then be fed into otherwise classical machine learning pipelines as a specialized quantum-assisted component, rather than replacing classical learning methods wholesale. This pattern of an initially dramatic-sounding claim being narrowed, refined, or partially walked back once subjected to careful scrutiny shows up again and again throughout the history of quantum computing, and it is worth treating as a general lesson rather than a criticism specific to any one announcement or company. Genuine scientific progress in this field tends to look less like a single triumphant breakthrough and more like a long, iterative back and forth between ambitious claims and careful, sometimes deflating, verification, with the overall trend still moving steadily forward despite the occasional correction along the way. A healthy approach to following quantum computing news involves neither dismissing every new announcement as overhyped nonsense, nor accepting every headline at face value without asking what a rival research group might say in response. The physicists working closest to this technology tend to hold both attitudes simultaneously: genuine excitement about where the field is heading, paired with disciplined skepticism about any single claim until it has survived a proper round of scrutiny from people with every incentive to poke holes in it. That balance, excitement paired with rigor, is ultimately what makes quantum computing worth following closely over the coming years, rather than treating it as either a solved problem already delivering on every promise, or empty speculation destined to remain permanently theoretical. Somewhere between those two extremes sits an active, genuinely difficult engineering and physics challenge, being worked through carefully, one experiment at a time, by researchers who understand both how strange the underlying rules of quantum mechanics really are, and how much careful, patient work still stands between today's fragile prototypes and the transformative machines so often promised in the more excitable corners of technology journalism. So the next time you hear a headline claiming quantum computers could break every code protecting the internet, or simulate the entire universe, or unlock secrets physics has chased for a century, it is worth holding two things in mind at once. First, the underlying science genuinely is extraordinary, confirmed through decades of rigorous experimentation, capable of producing results that sound almost like fiction precisely because they describe a layer of reality that never evolved to make intuitive sense to a species built for tracking spears and predators. Second, the actual engineering required to fully realize that potential remains a serious, ongoing challenge, measured in careful increments of qubit counts, error rates, and coherence times rather than sudden, overnight transformations. Both of those things can be true simultaneously, and holding them together. Rather than collapsing the story into either blind hype or dismissive skepticism, is the most honest way to understand where this remarkable, still unfolding chapter of science actually stands.